Assalamualaikum and good day, madam. My name is Muhammad Lukman Zazri. My message number is 10DTK22F1044, and today I will present to you my presentation titled Semiconductor Part 1. In this presentation, we will talk about rectifiers and bias voltage. Now let's get started. A PN junction is formed when a P-type semiconductor material is brought into contact with an N-type semiconductor material. When a voltage is applied across the PN junction, it can be either forward biased or reverse biased. So, in forward bias voltage condition, the positive terminal of the voltage source is connected to the P-type semiconductor material and the negative terminal is connected to the N-type semiconductor material. This causes a flow of current across the junction as electrons from the N-type material move towards the P-type material and holes from the P-type material move towards the N-type material. As a result, the depletion region, which is the region around the junction where there are no mobile charges, becomes narrower. In this condition, the PN junction allows current to flow easily and has a low resistance. Now, in a reverse bias voltage condition, however, the positive terminal of the voltage source is connected to the N-type semiconductor material, and the negative terminal is connected to the P-type semiconductor material. This causes a depletion region to form around the junction, as the electrons from the N-type materials are repelled by the positive terminal and move away from the junction, while the holes from the P-type material are repelled by the negative terminal and move away from the junction. As a result, the depletion region becomes wider and the PN junction does not allow current to flow easily. The PN junction in this condition has high resistance. And now, let's move on to the rectifier. There are two types of rectifier that we have learned, which is the full wave rectifier and the half-wave rectifier. A half rectifier circuit is a simple circuit that allows only half of the input AC waveform to pass through the output. The circuit consists of a single diode and a load resistor connected in a series across the input AC voltage source. The diode is connected in such a way that it conducts a current only when the input voltage is positive. During the negative half cycle of the input voltage, the diode blocks the flow of the current, so the output voltage will be zero. The output waveform of the half-wave rectifier circuit is pulsating DC voltage, which means that the voltage rises to the peak value of the input voltage during the positive half cycle and falls to zero during the negative half cycle. The output voltage is not constant and it is affected by the input voltage amplitude and frequency. Meanwhile, a full-wave center-tap rectifier circuit is more complex circuit that allows the full input AC waveform to pass through to the output. The circuit consists of a transformer, a center-tap secondary winding, two diodes, and a load resistor. However, in my diagram here, it shows 4 diodes, but it still works the same. During the positive half cycle of the input voltage, the upper diode conducts the current flow through the load resistor from the top of the secondary winding. During the negative half cycle of the input voltage, the lower diode conducts the current flows through the load resistor from the bottom of the secondary winding. The output waveform of a full center-tap rectifier circuit is relatively smooth DC voltage, which means that the voltage remains constant and does not fluctuate as much as the output of a half-wave rectifier. The output voltage is affected by the input voltage amplitude, frequency, and the load resistance. In summary, a half-wave rectifier circuit allows only half of the input AC waveform to pass through to the output, resulting in the pulsating DC voltage. A full-wave center-tap rectifier circuit allows the full input AC waveform to pass through to the output, resulting in a relatively smooth DC voltage. Alright, that is all for part 1 of this semiconductor presentation, and thanks madam for listening to my presentation, and I will see you in part 2. Thank you.